Welcome to the Empowering Tomorrow's Automotive Software Podcast, brought to you by ETAS, a single source of cutting-edge software and hardware solutions that make automotive embedded systems safe, smart, secure, and sustainable. Each episode, we'll be joined by ETAS and industry experts to discuss how electrification, automation, and connectivity are impacting the automotive industry. Now, sit back and enjoy the discussion.
Hello, everyone, and welcome to another episode of Empowering Tomorrow's Automotive Software from ETAS. I'm your host, Suresh, and I'm happy to welcome Sangeeta Theru today, a recognized leader in the virtualization and automotive verification platform from Stellantis. Sangeeta currently leads the virtual validation platform at Stellantis, and she's the driving vision and execution of the engineering workbench solutions. Sangeeta comes with many years of hands-on experience in hardware in the loop, software in the loop, and validation testing. And she has played a pivotal role in moving the industry from hardware development testing towards software-first environment testing. In today's episode, we will be diving a little bit into virtual validation and how we can use virtual ECUs to shift left and reduce our reliance on hardware-based hardware in the loop benches and vehicle-based testing. Sangeeta, welcome to the podcast. It's great to have you here.
Thanks, Suresh. It's great being here. And I think this would be a great opportunity to deep dive into the SIL topics and virtual validation at scale.
Yeah, today I'd like to talk a little bit about how software velocity is outpacing hardware, right? Meaning, how can we move testing and validation further up the validation chain so we can get to the market faster without relying on having to get hardware available to us? And the other thing is, I want to focus a little bit about how hardware in the loop can be considered a bottleneck, but not a strategy. How do we bypass that? How do we move forward? And then positioning virtual validation as an inevitable means of developing software rather than experimental. So what I want to focus on first, Sangeeta, is a little bit about why does Stellantis and the industry in general want to shift left? What is the driving factor that you see that's making you make this change?
Absolutely, Suresh. I think the first thing, again, we have to understand here is why are companies, let alone only automotive, right, pushing digital validation so hard? Actually, right now, a lot of focus has been there on how to shift left, digital validation. This world of simulation is not new to automotive industry, right? We've been using simulation methods quite extensively in a lot of our development activities right from the beginning. If you talk about CAE analysis for vehicle dynamics, performance, structural crash performance, so on and so forth, all of these concepts have been used in early development processes, especially in the automotive industry, very early on. But what is different right now is how do we scale this? How do we move this virtual need and virtual development into a complete system-based, integration and testing, right? With software as a focus, because again, software is becoming big right now. We are basically moving into a world where mobility, mechatronics is all merging together, right? And right now, the focus is more on how to begin like early virtual validation at a system level. Okay. So, one of the major things is obviously speed. We don't want, like systems to be developed and validated at a very late phase in the process, in the vehicle development process. We want to condense that shorter, and so that we can integrate earlier, we can test earlier, so that we can prevent risks. What if our system fails? Can we find those issues earlier on in the process so that we can fix it early to prevent late detection of issues, which adds on to like cost, warranty, all of the challenges that we have to face from a root cause analysis and also fixing at a very late phase in the process. The Again, I alluded a little bit from the development cost standpoint, but also in the early development processes when the hardware doesn't exist, right? And typically we end up with such kind of situations, right? ECUs may not be available. The chipset is probably under development, right? And in such kind of scenarios, does software development need to stop and wait for all of this hardware development to complete before we can start validation, right, or start development? My answer to that is no, right? We should start development even when hardware doesn't exist because it gives us the leverage to be ahead of in the cycle. And so with that comes, okay, what is the benefit of having virtual validation when hardware does exist, right? And obviously, cost of physical prototypes is way higher if you want to start development and testing in an integrated environment. Building such kind of system hills, or building system or vehicles, building vehicles is going to be costlier, and it's definitely better to do such kind of development work and validation work using software in the loop platforms early on. The other one is the scalability, right? All of your test scenarios and corner cases that you want to kind of like validate in a vehicle environment. Can we even do that? Can we even exercise the bandwidth of the test cases that we want to test in a vehicle in an actual vehicle environment? ADAS is an example, right? All the autonomous features that we want to test in a vehicle, can we actually do that in a complete vehicle environment? We have to move some of that testing into a more virtual environment so that we can exercise the system again very vastly. And then comes, again, that talks a little bit about the scalability. Also talking about like the variant management. It's huge. We are a company with 14 brands spread out globally, right? So, and we have a lot of variations between vehicle to vehicle, brand to brand. Can we basically, test one variant and call it a feature set that will be applicable to other variants? We cannot. And taking the variants into a development process, can we build vehicles? Can we build physical prototypes for all the variants that we are building, right? And so this is where virtual validation really, really becomes a game changer. So with that, I think we can go into a little bit of a detail. I think your question was more about hill versus sill, right?
Yeah, maybe I have a follow-up question there, right? I
Sure.
think you mentioned you want to be able to find issues before hardware even exists. Someone like myself came from very much a hardware testing environment. We validated everything at a system level on a car or on a physical ECU to convince people like me or others like me, right? What kind of issues can you find in a software in a loop virtual environment that can basically ease the burden of having to retest it or validate it on a physical hardware? And what is the confidence level of doing that?
That's a great question, right? I think it's a very common problem statement, at least in this, when we talk about, hill and sill, right? So far, what we have identified is the biggest hurdle is not the tool capability, right? We already have SIL platforms running at scale. It is the confidence and correlation between what runs virtually versus how does that compare to an actual fault, actual issue that I figure out in the hardware system, correct? So again, engineers like yourself, like you mentioned, are going to be trusting a virtual ECU only to an extent, or even a SIL platform, only to an extent that it is proven by back-to-back testing, repeatable, right? You run one test, does it provide the same results the second time? And also can provide the similar results like a physical ECU or a physical system under same conditions, right? Getting to the point, I think it's got several, enablers, several reasons. And in general, I don't think it's the exact resemblance between physical hardware and software in the loop that we have to really go behind as a validation point, right? We'll talk about it a little bit.
Mhm.
But answering your question about what is fundamentally, what could we test in an SIL platform, any testing that does not need timing determinism, right? Anything that does not need that cycle accurate realism between hardware and software. I think that's something where we move the testing into a hardware environment, a test bench, an HIL, so on and so forth. Because if you think about it, physical ECUs do have, jitter. You have the instruction set, service routines that kind of like, have to interact correctly in the system so that you can execute a function feature accurately in the right order also, right? They may also behave very differently under thermal stress or even in a stress condition, voltage, thermal stress. All of these testing, need to happen with the physical ECU. CPU bandwidth, that's another great example, right? I don't think you can move such kind of tests into a complete virtual validation environment. But that being said, that's typically about 20 to 30% of the testing. What can we do for the remainder of the 70 to 80% of the test, right? We have to use SIL platforms. Why? Because we don't need instruction accurate, cycle aware test execution in order to test the remainder of the 70 to 80%. I'm talking more about the functional validation, feature validation that you typically do at the vehicle level or even at the ECU level, be it even component, right? But the bigger bang for the buck comes when you start integrating more and more ECUs at an earlier phase of development and you start early integration tests in an integrated environment with virtual ECUs, plant models, bus communication, and also throwing in the test scenarios, the road models, environment models, everything to test specific feature functionality, be it autonomous, be it infotainment based, body domain, so on and so forth. I think that's the biggest advantage of using virtual validation, especially in a SIL environment.
So I think this leads to a perfect next question. I think we talked a lot about virtual ECUs and virtual validation. How do you define a virtual ECU, right? We've heard of level one, level two, level three, level four. My understanding is level one, level two, you can do application layer type of activity. But we're talking about software in the loop with this level of detail. What value do you see in type 3 and type 4 virtual ECUs, or level 3 and level 4 virtual ECUs, that help close this gap between what an HIL or hardware in the loop system would do and what a software in the loop system can do? So what are we really unlocking in terms of system level confidence with like this type 3, let's say type 3 virtual ECU?
I would expand this into even type 3 plus, which is
Mhm.
another topic of discussion here, right? So, again, going back to the definitions of what level 0 to level 5 ECUs are, level 0 is basically controller models, a subset of application models that you will run typically in a MIL environment or an early SIL environment. Level one will include some application code, right, for test coverage of application software (ASW). Level two may contain some simulated based software included in the VECU. Level three comes where there is production based software integrated with the production application software as an integrated package, basically wrapped up, built for x86 target, right? Where typically we're talking about classic AutoSAR, where the MCU layer is emulated, and you basically have any layer above the MCU or the MCAL layers real, right? All of the software code that goes into the target ECU. So that's level three. And then level four VECU is where you have typically like hardware models, be it SoC, an MCU, or even the peripheral models, right? All of that simulated on a computer environment, on an x86 or an ARM Graviton, instance, and you basically have the code flashed directly as an executable onto these models. Now, something in between level 3 and level 4 is level 3 plus. And what does that mean? It's very similar to level 3 production based software, but more fidelity drawn into the lower layers of the hardware, not generally the actual SoC or the MCU model with peripherals running, but more so maybe an ARM SoC, actually modeled on cloud. It may not be the actual plan of record SoC or MCU, but it could be close on target, especially for simulating or emulating the infotainment systems or camera based systems, autonomous systems, which brings in a little bit more fidelity into the software layers that we want to build and deploy and test on cloud, right? And also bringing in the hypervisor layers directly onto cloud versus using the same hypervisor on hardware targets. So that's what we define as level 3 plus, and I know industry uses various definitions of this. So going into where are we seeing our biggest benefit and what's the typical use case of level 3, 3 plus as compared to level 4, right? And level 5, again, it's real ECU with target hardware. Level 3, 3 plus is where we have found the sweet spot, where we can get the cross compilation of our actual software, actual source code, against an x86, an ARM, or an ARM core target. And the evaluation between speed of how the simulation runs versus the performance, right? Or the testing that we have to do at the subsystem or the system level, we find the benefit when we build level 3 and level 3 plus VECUs. I think that's a learning from Stellantis side, right? Because when we get into level 4, since we are actually building the target SoCs, target MCUs, and the peripheral as models, they tend to run slower, and they tend to, not, especially when you start integrating these ECUs in a system environment, it makes the simulation run very, very slow. And especially in a CI/CD environment, or even for a developer use case, that this becomes a kind of like a user experience that is not really very wanted, right? So level 3 and level 3 plus run much better and strike the balance between speed and performance is what we've learned. Running at scale, and at the same time running at a target speed that is very useful for a developer or a testing engineer to get results faster. And even introducing these in the CI/CD workflows where we can run nightly builds, nightly test cases, I would say that's the sweet spot.
So I think I'd like to explore that a little bit, right? You mentioned, virtual ECUs running on x86 targets or ARM Cortex targets, whatever it may be, Graviton, right? But my assumption is that these are not desktop use cases anymore. We're not running them on a PC. We're scaling them to some kind of cloud capability.
Mm-hmm.
In the software in the loop environment, how many tests are you able to run in parallel? What does that scalability look like? And how does it integrate into a CI/CD pipeline? Are these tests done all headlessly, right? Are they scripted based CLI tests? Or is there someone actually able to use a GUI, see what's going on? Or is it done after the fact where you get the results and then you visualize it? What does the deployment look like going from a traditional PC based testing to a scalable cloud integrated testing? What does that environment look like?
To answer your question, I think it's more distributed, right? Again, there are different user communities on how the users use the platforms. I would say the development community who have hands-on code, who are building code every second, they tend to and want to test the code right away. They they have or they like the manual interaction between the SIL environment and their test that they want to run on this environment. Make a change in the code, build the code, integrate the platform, and run a manual test. Understand if the change that they made actually resolve an issue that they were trying to resolve, or basically going back into whether it met the feature requirements, right? But that portion of user community is, I would say, getting less and less as we move into more automation and CI/CD DevOps practices, using DevOps practices in automotive software development. Here, I think SIL platforms at scale become really a huge enabler, because what we have actually proved out is test cases run at scale, on the cloud every night, built and integrated as a platform and run on cloud nightly. And this is completely headless, right? Yeah, you're starting off your workflow with just pushing the code into the changed code into a workflow where pipelines and automation kind of like takes it from building of the software to the platform building to running, deploying like the platform so that you can grab the test cases that you want to run on this platform, all the way up to like publishing test results. And the engineer basically comes back the following day morning to analyze the pass and the failed tests so that they can, bring in the new software, rerun some of the tests that they found failed for root causing and other purposes, right? So what we have figured out is with SIL, we are able to parallelize this testing, pull in more instances, right? Run these instances more seamlessly for this end-to-end workflow that we are talking about. This is the comparison we've done. At least the deployment, testing, basically providing the results, runs completely headless. And it has proven to be a much more usable use case within Stellantis than actually the manual testing. But of course, again, it's a split. For a developer use case who wants to see results every for the change that they have done, they use manual testing. But a majority of that is also moving into like automated test cases, run overnight, so on and so forth.
So even hardware in the loop can have automated testing, right?
Yep.
So is there a possibility to have like a hybrid approach where you do an X number of tests on a software in the loop system, and then immediately it can trigger a set of sequences or a set of tests in a hardware in the loop? Can this all also be automated and kind of housed in a cloud-based environment where not only are you getting the virtual target, but you also get some results out of the physical target?
Absolutely. I think this is where the split between 70 to 80% on virtual versus 20 to 30% on the HIL. This study, I mean, this result that came out of the study, I think it's very important because exactly to your point, we can run parallel agents, SIL agents, to cover 70 to 80% of our testing. And simultaneously, we can filter out any of the hardware-based tests that you have to perform and scale this on the hardware in the loop environment parallelly again. But you will use less number of HILs as compared to the SIL agents that you would use.
So I think this kind of goes into my next section of questions, right? You can almost use the hardware in the loop or HIL kind of as a verification for some engineers to feel comfortable that the results are validated from the SIL. But in my opinion, I think talking to many people around the industry, also within our own organization, the hardest blocker I see is getting people to believe that this is the right way to work, right? That this is a trustworthy and validated version of results that can be used to make decisions. I see that there's a gap. Yeah, there's a gap in trusting the virtual results. An engineer typically comes from ownership, right? They own a feature, they own a function, they've tested it, they validated it. In the modern world, you may code it, but you push it to the cloud, someone else is validating it, or some entity is validating it, and it's being consumed and pushed forward. In your role, how have you been able to successfully or even unsuccessfully convince people that this is the right mindset to shift left? How do you encourage people to try this and believe in it? Because as you stated, this is a vital way for us to get to market faster, right? This is the way we are going to reduce our development time. But there's always going to be a bottleneck in the people and their personalities. What have you seen in your experience that has kind of helped mitigate that gap, or lessons learned for people to understand going forward?
That's a great question, Suresh. I think it's the psychological trust versus technical trust, right? It's one of the biggest, I would say, challenges that we face as an industry, right? Coming from a very traditional automotive OEM, I myself I started my career testing and developing in vehicles. And I grew my interest to virtual validation and development through experience and through, really understanding what benefits does simulation actually can play in doing things earlier in a more easier way than, waiting for vehicles, waiting for prototypes to be built, or even changing vehicles for rapid prototyping purposes, right? Where typically I will probably not be able to complete my testing that I want to do in a particular day because of a number of challenges that could occur. So it's always the balance between what do I want to accomplish versus what can I accomplish. So, as a senior engineer, right, we all learn to debug in a very hardware based environment, probing pins, oscilloscopes, right, hardware in the loop systems, basically to understand hardware modes, failure modes very intricately, and things like that. So, for those people, obviously, this whole topic of virtual ECU is going to feel more abstract. I mean, it's a software problem, right? It's not a hardware problem,
Right.
correct? So how can we mitigate this? And again, I'm sure this is a common challenge, right? And how do we mitigate this? Obviously, this needs to be very closely driven by both a team that is delivering these platforms versus the team that is actually on the receiving end, trying to work through their daily work, daily whatever they do in the hardware, and slowly and steadily moving those test cases or testing into the environment that is now completely virtual, right? So the responsibility is distributed here, the push and the pull, right? The back-to-back testing, trying to prove out that the virtual environment actually resembles a hardware-based environment. I think that responsibility is definitely upon a platform team, right? For example, my team will be responsible for making sure that we are able to prove that, yeah, hardware behavior and the software behaves, or SIL behavior is very similar to what we are seeing on the hardware in the loop, right? But even more so, making the workflows more seamless for our customers, more easier, similar workflows like, for example, providing debug capabilities, breakpoint capabilities, trying to make sure that they are able to find faults, root cause very effectively in the software in the loop environment. So this goes back to the tool availability, right? So tools that they are typically used to using in the hardware in the loop environment, how can we provide a similar capability in the SIL environment? I think focusing on those things. Another example could possibly be like in an HIL, the test engineer, since the hardware is all connected, the electrical connections already exist, the test engineer is responsible for flashing the software on the ECU, just like how they would do in a vehicle too, right? The test engineer is basically going to do that. They're going to run a certain level of tests, and then they're going to troubleshoot if the issue is on the HIL or is it a true product issue, right? But how do we make sure that we are able to, differentiate that and, basically make sure that the workflow enables the same test engineer to flash not a target software, but a VECU, but the workflow is the same. That is very critical. Building an environment and giving the capability for a test engineer to, or providing the tools for the test engineer to flash the software just like how they would do on an hardware in the loop. Those are the kind of details that make the workflows much seamless and automated for a customer community. So those are all the things that we focus on as a platform team. But what is the responsibility of the test engineer, right? Or what is the responsibility of an engineer who is typically being used to the hardware in the loop? Again, taking the tests that they typically perform in the hardware, seeing what those test cases are going to be applicable to a SIL environment, and slowly and steadily making that transition into the SIL environment, building that trust slowly and steadily. And with automation, CI/CD, workflows, I understand the challenges of interfacing, software and into a hardware system, right? Automotive systems are mechatronic systems, so it's hard. It's hard, and especially when you talk about like I have a real hardware and I'm writing software for that actuator or reading a sensor. But we can bring in the CI/CD workflows, DevOps practices into this environment too. But it's the trust that the testing teams or development teams have to build slowly and steadily from their end.
Okay. So comfort zone is always a challenge, right? People, unless you force them, people tend to stay where they are most comfortable. If I feel I can test on my vehicle or on an HIL and I have my tools already, I'll continue to do so. What organizational levers can a company push to make this change or force the change, like reducing the number of hardware or reducing the number of vehicles? What kind of measures do you see that are ways to encourage or forcefully encourage some people to make the change so at least they start using it?
I would say, instead of using the word forcefully, right? Um, it's how do we get the user community to embrace this new technology and actually start using it in their workflows, right? So again, this is also twofold. There is the top to bottom and bottom to top, right? It has to come from both directions. The top leadership has to embrace this and, just like you said, have the right questions, to the engineers, to the leaders, to the managers, about, are you using the right methods for development and testing? I think that's the responsibility of a leader, right? When you're talking about top down. And when you talk about the bottom up, it's basically how can I do my job better? Because again, I may not end up having an HIL freely available or a vehicle freely available for doing my job all the time, right? How can I be more efficient in doing my job? And that constant, curiosity and thirst of, finding these new technologies, new tools that can help their workflows to be more easier, more seamless. So it needs to come from both ends, is what I think, right?
Mhm.
Some push from leadership by measures of, reducing the number of vehicles, reducing the number of hardware in the loop systems that can be deployed for every programs. And I think, again, I don't think we can sustain this, especially thinking about the enormous number of, the variants that we have, correct? The cost versus how much we have to test, especially keeping quality in mind.
Mhm.
I don't think we can sustain that with all hardware testing. So it's basically the push from leadership to say, hey, you know what, we're going to use only certain number of vehicles or hardware in the loop systems, subsystems, vehicle hills, whatever the systems are, right? Plywood box in the validation and development process, and at the same time, the engineering community, the engineers to start thinking about how efficiently they can use these methods and platforms in their day-to-day work.
No, that makes sense. So I guess the last question or last information to share here is, what does the future look like? We've talked a lot about where we're heading, what you're doing today, some of the challenges we faced along the way. Assuming we can scale and assuming that this grows, what does the acceleration look like? What does the end product look like? What is your vision of what this could be?
I think virtual validation is already happening. Okay, so it's in a pilot phase, is what I would say at this point of time, right? The next step is to understand how we can, integrate more and more ECUs, more and more systems that cover more of the testing that you would typically do in a vehicle, right? Cover multiple domains, ADAS, body, infotainment, chassis. How can we bring all of this testing into a more virtual environment, right? In a system environment. We talked about how simulation has already existed, but now we're talking about truly doing testing and development in a system environment, right? So I would say we're moving towards this goal of a virtual vehicle, and again, we can talk about what does a virtual vehicle mean? Do I really need to build the entire vehicle on cloud? I don't think that's what I'm stating. It is, what do you need to test for what purpose, right? And again, this differs between a team member, a calibration team member, a development software developer, a systems engineer, an architect, so on and so forth, right? So building a virtual vehicle that is trusted enough by the engineering community so that we can make this engineering and business decisions with no physical prototypes needed for development, for learning, right? But then you still need to go into a physical environment for confirmation, for certification, so on and so forth. I mean, do I need a physical system for architecture freeze, for software freeze, right? Hardware sizing, safety concept. I don't need a physical environment for this, all of this, right? We can move all of this into a more virtual development first, get to a point where you have to move into a physical environment and close that correlation loop by running tests in a physical environment. And not doing that only in like single ECU environments, but just scaling that into subsystems and beyond to cover a majority of the vehicle validation requirements. I think this is what I see as the future, and building the tools that lay underneath that can make this more seamless, right? Even from or efficient, optimized from a platform development standpoint. Bringing in what I call as a system OS concept, bringing that into production and scalable environment.
Perfect. That's a great vision, I think, for everyone to kind of understand and see how they can grow into that environment. With that, I'd like to thank you, Sangeeta. It was a great discussion. I think we got a lot of insights today on how virtual validation is being scaled at Stellantis and also what it could mean for the future of automotive software development. Again, thank you for participating and hope to do it again soon.
Thanks, Suresh. Thanks, Itas, for this opportunity. Great discussion.
Yes.
Thank you for joining this episode of the Empowering Tomorrow's Automotive Software podcast. Please leave a comment or review with your feedback or what you'd like to hear in future episodes. To learn more about automotive embedded systems and ETAS's capabilities, visit our website at ETAS. That's ETAS.com.